We're now going to look at some basic rules that are going to help us calculate limits. And I'd like to start out by just kind of informally introducing a few of these rules and then kind of show you how they're used in a simple example. And then we'll actually show you what all the rules are that are given in the textbook, and then use them to calculate some limits. So here's some basic rules that really make sense. The first two do for sure, and so that is we can call it the limit of a constant. And so let me kind of give you an example. Let's say I had y is equal to 3. Right? 1, 2, 3. That's a horizontal line. Y equals 3. And if I had any value down here, like let's say -2, right? If I wanted to find the limit as x approaches -2 of just 3, well, as you approach -2 from both sides, the function is obviously approaching 3, right? Because it's actually 3 for all the values, right? And so you basically get this general rule here that the limit of a constant as x approaches c, so limit of a constant as x approaches c is just equal to that constant, whatever the constant is. Okay? And that makes a lot of sense. So here's another rule. We'll call this limit of just y equals x. Okay? So clearly if you have the graph of y equals x, right, it would look like this. Y equals x. And then let's say we want to know here 1, 2, 3, 4. So let's say we want to know the limit as x approaches 2. The limit as x approaches 2 of just x is equal to what? Well, as you get closer and closer to 2 on either side, this graph is getting closer and closer to 2, right? As you get closer and closer to 4, the graph is getting closer and closer to 4, right? So basically the limit as x approaches 2 of x is just equal to 2. Okay, and in general, the limit basically in general, the limit as x approaches c of just the function x is equal to c, right? Okay, so those are two rules that really make sense. Those are pretty obvious. Now, here's a couple rules that maybe aren't quite as obvious, but they're believable, and they would be the limit, and I'm just going to write these rules out in general. The limit as x approaches c of f of x plus g of x. So if you got the sum of two functions, the limit of that sum of two functions is actually the sum of the two limits. So the limit is x approaches c of f of x plus the limit as x approaches c of g of x. Okay, and that's believable. Okay, this is approaching its value, this is approaching its value, and if you add the two values that the two are approaching, you should get the limit of what the function of the sum of the two values of the sum of the two functions would be. Okay, so this is believable, and the other one is the following, and this we call this is like the limit of a sum, right? This would be the limit of a constant multiple. So if I have the limit of some constant times f of x, okay, then what I can do is I can pull this constant out and just take the limit as x approaches c of f of x. Okay, And so this constant multiple rule just says you can pull the constant out, and you can take the constant times the limit of f of x. And that's going to give you the same thing as the limit of some constant times f of x. And we could call that the constant multiple rule. So all four of these rules here, you could actually prove using the formal definition of a limit. Okay, with the epsilons, deltas, the definition that's in section 2.3. And they're not, these proofs are not trivial. The formal definition of a limit is a very difficult definition to both understand and use, but that's where it would come into play. It could prove these rules, that the limit of a sum of functions is the sum of the limit of the two functions. The limit of a constant multiple times a function is the constant multiple times the limit of the function. And then once you've proven all these rules, then it would be easy to find all kinds of limits. Okay? And so let me just give you an example of the logic behind this. So let's say I want to find x, the limit of, as x approaches c, of, let's say, 2x minus 1. So a linear function. Okay? And even if you wouldn't do this every time, this is the logic. Using this rule here, I could separate this into the limit as x approaches 3 of 2x minus the limit as x approaches 3 of just 1. And so the limit of this would work with sum and difference, actually. And so I can split this up over a difference, like this. Okay? And then this has a constant multiple, so I could pull that out, and I would get 2 times the limit as x approaches 3 of just x, right? Minus the limit as x approaches 3 of 1. And it would look like that. And notice that this is that identity rule, and this is the constant rule. So that's these two rules right here. So then what I could do is I could take, this would be 2 times whatever the limit this is, and that would be 3, right? And then the limit of that is just 1. That's a constant, and so it's equal to the constant. And it would look like that, and this would be 6 minus 1 is equal to 5. So the limit of this as x approaches 3 is equal to 5. And also notice that this ended up being, it amounted to just plugging 3 into this function. Do you see that? So if I would have taken 3 and plugged it into the function, okay, I would get the limit. Okay, so, and this would work for any linear function. It would work for any linear function because I could do this with all linear functions. Okay, but the reason it works is that these rules here are true for limits, and I could apply it to an expression like this in this sort of way to get the limit. Okay, so it's these rules that tell me that if I have a linear function, really I just need to plug it in and I'm going to get the value of the limit. Okay, so that's the logic behind some of these rules here. And so we're going to add to these rules. So these are the ones that the book gave you, and we're going to just stick with this. You could probably create some other rules that could be proven as well, maybe ones involving the trigonometric functions or whatever, but we're just going to stick with this here. So this is the constant multiple rule, that the limit as x approaches c of some constant is just equal to the constant. This is the identity rule, the limit as x approaches c of x is equal to whatever c is, whatever you're approaching, right? The constant multiple rule means you can pull constants out of the limit, right? So you have this, and you can pull that constant out of the limit, like this, and take the constant times the limit of f of x as x approaches c. Then you have this sum difference rule, which we use, which is the limit as x approaches c of the sum or difference of two functions is the sum or difference of the limit of the two functions. Okay, you can also do a product rule where the limit as x approaches c of the product is equal to the product of the two limits. Same idea, you can split this up even over a product. Okay. Now, if you've taken calculus before and you've learned all those shortcut rules, it's kind of dangerous. The book called this the product rule. This is not the product rule for derivatives. The product rule for derivatives is a lot different than this. This is kind of a product rule, and then you could say for limits. So don't mistake it as the product rule that you learned when you were learning the shortcut rules for derivative. And same here, this is like a quotient rule. This is quotient rule for limits, okay? And basically this is saying is if you got the limit as x approaches c of a ratio of two functions, one function divided by another, again, you can just split the limit up, provided that the limit as x approaches c of the bottom function does not equal 0. Okay, if it equals 0, then you cannot necessarily just do this. In fact, you would be taking the limit of this divided by 0, which is undefined. Okay, so but if the bottom does not equal 0, then you can just take the ratio of the two limits. Okay, and then these are similar. This is like a power rule, and this is for n equals positive integers. Okay, so this is like, squared, cubed, 4th degree, 5th degree. And basically it's just saying if you're taking the limit of some function raised to a power, then what you can do is you can take the limit of the function and raise the limit to that power, and you'll get the same thing. So it's kind of like this constant multiple rule in a sense. Okay, but it's with the power. And then you can do the same thing with a root here. If you got the limit as x approaches c of the nth root of f of x, well, you can take the nth root of the limit as x approaches c of f of x. So you can just find this limit, and then you can take the nth root of that. Okay? And so with this, you can do quite a bit. Also, I should say here that this, if n here, first of all, n has to be a positive integer here, but if it's even, then when you do this limit, it has to be, f of x has to be positive around, for an interval around c, okay, because you can't have a negative number underneath the radical. So you do have to make sure f of x is positive around where you're taking the limit, okay? But otherwise, these rules here are really helpful, and you can use them to do quite a bit. And let me show you just kind of the logic here. Not that you would need to write this out every time like this, but this helps you see the logic. So if I have this, I could rewrite this as the limit as x approaches 3 of 2x squared minus the limit as x approaches 3 of 3x plus the limit as x approaches 3 of 5. So I'm just splitting those up. That's the sum difference rule. Okay, now I can do a constant multiple rule here. So I'm going to pull out the constant multiples. 2 times the limit as x approaches 3 of x squared, right, minus the limit as, minus 3 times the limit as x approaches 3 of x, plus, now the limit of a constant is just equal to the constant, so I can write 5 there. Okay, and now what I can do here is I can use the power rule. So this would be 2 times the limit as x approaches 3 of x, right, raised to the second power. So this is what the power rule would say. If I'm taking the limit of this power, then I can take the limit of what's being, of the base here, raised to that power. And then this would be minus 3 times, now this is the identity rule, so that would just be 3. And then this would be plus 5. And now this is just the identity rule, so I could rewrite this 2 times 3 squared minus 3 cubed plus 5. And and then I can calculate this. So this is 9, 18 minus 9 would be 9 plus 5. This is 14. And that would be the limit, okay? But again, notice this is the logic here, but this last step kind of reveals that what I ended up doing was putting 3 into my polynomial, right? And so really I'm just evaluating this at 3. And these rules are going to work for any polynomial. It doesn't matter how high or how many terms there are or what the degree is, because this power rule will work for any power. You would just split them up like this, pull out constant multiples, do the power rule as many times as you need to, and it'll end up with something that looks like you just plugged in x into the polynomial. So when I actually find the limit here, I don't write this out every time. You know, I just evaluate the polynomial, knowing that for any polynomial I can do that. Okay? But you might want to write it out a little bit just so you know that you understand the logic behind it and you don't misapply this in situations where you're not able to do it. Okay? So let's try it with this. This is a rational function here, one polynomial divided by another. So what I can do here is I can use the quotient rule and take the limit of the top divided by the limit of the bottom, provided that the limit of the bottom doesn't equal 0. So if I plug 1 into the bottom, I get 2. I don't get 0. So that means I can split this up. So this would be limit as x approaches 1 of x squared minus 4 divided by the limit as x approaches 1 of x plus 1. Right? And I can split this up because this limit doesn't equal 0. So, of course I could split all this up. Maybe I'll just do it all in one step here. This would be the limit as x approaches 1 of x, that quantity squared, minus the limit as x approaches 1 of 4 over the limit as x approaches 1 of x plus the limit as x approaches 1 of 1. And then this would just be equal to 1, so I'd get 1 squared. This would just be equal to 4 minus 4. This would just be equal to 1, and that would just be equal to 1. Okay, so really it amounts to just plugging this into the rational function, right? So 1 minus 4 divided by 2, so negative 3/2 would be the limit. Okay, and so again, if the limit doesn't make the denominator equal to 0, then you can do any rational function as well by just plugging in the number. And by rational function, I mean one polynomial divided by another. Okay? So now let's do maybe a couple that are a little more complicated here. And what's more complicated about these is I get a 0 in the denominator. Okay? So if I plug in 1 into here, I would get 1 squared is 1, minus 1. 1 minus 1 is 0, and that would be undefined. So I cannot use the quotient rule. I can't divide them up, right? So, but what I can do is I can simplify this, and if that helps, then I can keep using the rules, okay? So this would be the limit as x approaches 1, and I'm going to factor that top, and it looks like I get x plus 2, and then x minus 1. And so if I FOIL that together, I get this. And then this, I can factor out an x here, and then I get an x minus 1. Okay, so there's no problem. I can do this. The limit of this is equal to the limit of this. And, of course, I can cross these out. I can simplify this however I need to. and I'm left with this. Now look, I can plug 1 in to the denominator and I don't get a problem. It doesn't equal 0 anymore. Okay, so then I can split this up. This would be the limit as x approaches 1 of x plus 2. The limit of x approaches 1 of just x, right? And then this will be just plugging 1 in there, so I get 3. And then this would be plugging 1 in there, I'd get 1. And so it looks like my limit is 3. So in this case, it's not just a matter of, oh, you can plug this in, because it is undefined. Okay, so this is not the same as that, but this has the same behavior as this for every value other than 1. And this one is not defined at 1. It has a hole in the graph. This one would be defined at 1. Okay, but you can do any of the simplifying you need to do, and if you can simplify it so that that denominator doesn't cause a problem anymore, then you can evaluate the limit. Okay, so let's try one more here. So I want to find the limit as x goes to 0 of this here. Now clearly I can't put 0 in the denominator because I'd get 0, right? So I can't just split it up. So what I'm going to do here is I'm going to use that little trick with the conjugate that we learned last time. So this would be x squared plus 100 plus 10, but then I have to do the same with the bottom. X squared plus 100 plus 10. So I'm going to multiply the top and bottom by this conjugate, and that's not a problem because this would be multiplying it by 1. So this would be the limit as x goes to 0 of, now when I multiply these two together, I get the square root of x squared plus 100, that quantity squared, minus 10 squared. Okay, so that's using the a plus b times a minus b is equal to a squared minus b squared. This is the a and that's the b. So then I get x squared times square root of x squared plus 100 plus 10. So then this would look like that. Now this would equal the limit as x approaches 0. Notice I need to keep the limit there each time here. It's easy to forget that. So this would just be x squared plus 100. This would be minus 100 all over x squared, square root of x squared plus 100 plus 10. Notice I'm making sure each step is equal to the next step. I'm not just kind of like, oh, that's too much to write, I'll just put a squiggle there, okay? Or I'll just write what I need to know to think about it to get to the next step. No, I'm writing that this is equal to this, is equal to this, is equal to this, is equal to the ending, and then I know I have the limit because each intermediate step is equal. Please take the time to do it. That's a skill that you need to build in order to do some of the harder problems where things get very, very complicated. Okay, and you will see that later on. So you need to be able to do that. Doesn't mean you can't skip steps as long as the next step is equal and you're able to do it in your mind, but it does mean that I want each one to be equal to the next. Okay, so now this 100 goes away. So now this is the limit as x approaches 0 of just x squared over x squared times square root of x squared plus 100 plus 10. So it would look like this, right? And I always remember, I got to keep that limit there. Limit as x goes to 0. So now these cancel out, leaving me with a 1, right? And now I got 1 over the square root of x squared plus 100 plus 10. And now, look, I can put 0 in this denominator and I don't get any problem, right? And so I'm going to go ahead and plug it in. and this will be just 1 over the square root of 100 plus 10, and that's 1 over 10 plus 10, which is 1/20th. So that means the limit of this here is equal to 1/20th. Okay, so now if you can't simplify this into a form where you no longer have a problem in the denominator, then it probably means that it doesn't have a limit, and it means that this is a vertical asymptote. Okay, but in this case, this would not be a vertical asymptote at 0. It would have a hole at 0. Okay, and then notice here, once I actually take the limit, that's what I did here. That's why I dropped the limit sign. So limit, 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 and now no limit. Why? Because I actually took the limit of this as x approached 0, and I got this. And now I'm just simplifying that. So there's going to be some point where you're just simplifying what you have there. Okay? So that's kind of how to use these rules then to find limits. So in the next video, I'm going to show you something called the Sandwich Theorem, and we're going to use it to derive a very special limit that gets used with trigonometric functions.